Hello everyone. Thanks. I'd like to just say thanks everyone for coming along. We've been organising this for a long time, and I was very worried that we get anyone coming along at all, and that we get all the speakers. So it's been a fantastic day as far as I'm concerned. I'm here to just quickly go through what we've been working on the past year or two, since the start of the society, and what we're going to be working on over the next year or so. And I would first, before I get started, like to apologise for the presentation and the talk. I was told I'd be doing this on Tuesday, and I've done it last night and this morning, so it's very poor. Keep that in mind, set your expectations suitably low, and we'll be just fine. Okay, so we're SpaceX. We've got two main projects. Now initially, the Society was founded to run this project here, xrt-c, Exeter Radio Telescope at Carridon. If you were here this morning for Wayne's talk, you've heard a little bit about that already, but I'll go through a brief history of it in just a second. We're also at the moment, the other main thing we're focusing on is this Half Tube balloon project here, and I'll go into a bit more about that as well. First off, I want to tell you a little bit about xrt-c. So the aims for xrt-c were, it's at its core a student-led project to build and run a radio telescope, 4.5 metre radio telescope, and the project aim was to do this for less than £10,000, which is actually quite ambitious. We wanted to use it to construct a load of different experiments at radio wavelengths, but first off, we want to do a survey of the galactic plane, where we will be essentially measuring the weight of the galaxy using the observations that we get. This isn't a new thing, but we believe that it's very unique for a project of its kind, i.e. there's very few other projects, if any, in the area that are even trying to build a radio telescope, and that's run entirely by students and for amateur astronomy. And one of the other driving forces behind the project has been to actually make this a very outreach-driven thing. So we've been trying to actually make this give it a long history of public outreach and education. So if you go to our website, xrt-c.co.uk, you'll see that we've documented the whole thing as we've been going along. So that's basically the crux of the project. So first off, I want to give you a brief introduction to radio astronomy, in particular H1 radio astronomy. Now, if you look at the galaxy, you'll see a whole load of different things, depending on which wavelength you look at. So if we look at the optical here, and you look at the galactic center, you'll see a load of stars as we come through the galaxy, but you'll also see a load of clouds here as well. So a load of the stars and the stuff in the galaxy is obscured by these dust clouds here, because the optical light can't get through. Also, if we look here, this is a near-infrared version, we see a very similar thing. You'll see that the entire galaxy is dappled with these clouds that are blocking out light. That's just due to dust floating in space. If we now actually go a little bit further, still into the infrared, this is glimpse, which is kind of mid-infrared, you can see that we're actually having these cool areas where stars are forming, glowing back at us. But these are still relatively warm. There's still stars there, giving them energy, kicking energy into them, which is causing them to emit. And even still, if we go cooler still into the sub-millimeter, we can still see these very, very rich star-forming regions that are glowing at about, was it 10 to 50 Kelvin, I think, somewhere around there. But still, there's still energy being kicked into them. But the problem is, there's a load of material in the galaxy that is behind all this gas and dust that is not observable because it's not giving off any light. There's no energy being kicked into it. So what radio astronomy lets you do is to observe this transition here. So if we have a hydrogen atom, we have a proton and an electron, and what they can do is they both have this intrinsic number called spin. And it's not, for those who are uninitiated with quantum mechanics, it doesn't mean anything. It's basically just a number in the mathematics. But essentially what it means is that if both spins are aligned, i.e. both up or both down, that's the two states they can be in, they have slightly more energy than if they're anti-aligned. So there's ever so slightly more energy if they're both the same than if they're different. And what can happen is that this is very, very low energy change. It doesn't take much to actually put it into an aligned state. But it's very unlikely that it's going to come back down from that aligned state. If you look here, we're looking at like thousands of... if you hold a hydrogen atom, just watch it. It's not likely to happen for a million billion years if you were to just watch it, which is longer than the age of the universe, I think. But it just turns out that just through sheer amount of hydrogen in the galaxy, the odds are in your favor. You just see the galaxy glowing back at you in this light as this spin flips and emits light of this wavelength here, 21 centimeter. So whereas I've showed you these here, you see that there's very little structure in the galaxy you can see. If you observe the galaxy at 21 centimeters, you see it just glowing back at you. We're just bathed in the light coming from the galaxy at this wavelength. So that is why we're wanting to observe at this wavelength. The other problem with it is that optical telescopes are relatively cheap in comparison, but radio astronomy is difficult because there's a load of other things to consider when you're taking the signal from the telescope and trying to do something with it on the end. So there's a load of expense involved in that. So I want to give you a brief introduction to basically xrt-c and how it's gone on. So the project was first basically conceived at the Norman Lockyer Observatory in 2010. It was originally intended to work with CubeSats that were being launched, but unfortunately both projects fell through and neither came to fruition for various different reasons. So the project moved, I think the fonts are missing if anyone's wondering why it's going weird. The project moved from the University of Exeter and it came and ran under the UK SEDS banner. SpaceX is a branch of UK SEDS. We formed it to basically run the project about 3 years ago. And the project itself was launched at the National Student Space Conference in 2013 by Freya and Susie, who are people who worked on the project. Unfortunately, we've had a load of blockades in our way trying to run this project, and one of them was finding a location for it. We wanted to build it on campus. We had no way of doing it. There was no space free due to all the development. We tried a load of different places to actually construct it nearby in people's farms, fields that they weren't using, and that was a no-go as well. But after months and months of searching, we finally found Carradine Observatory, and we finally managed to sign a memorandum of understanding with them in 2014, which let us build the radio telescope at the observatory. And so we move on to 2015, where we have the first foundations laid over here. That's a big concrete block that the telescope is on. We managed to get the mounting stand up and working, and we have struts as well to support it. And you can just see the dish just under construction in the background there as well. So 2015 was a very good year for the project because we finally got everything working. So if we now fast forward a little bit to 2016, we have the dish finally being mounted onto the stand, and the telescope actually taking shape. We've got counterweights there as well. So we can finally actually steer this massive 4.5 meter dish and point it at the sky. There's a video of this happening on YouTube. I have it here to show, but I don't think we've got enough time, so I'll skip on, and if you want to see it, it's available on our YouTube channel. If you want to see it. So move forward a little bit with the project stalls just a tad because everyone gets very busy as happens. And finally in 2017 we finish off by mounting the antenna at the focal plane of the telescope. And on the same day we achieved first light. So we finally, after 7 years of this project being conceived, moving on through a load of issues, we finally get first light on the project. And on the same day, the telescope broke. This is a sign of things to come. On that same day, the controller which controls the moving of the dish burned out, and we had to send it back to the Netherlands several times throughout the next year. So that's one of the things that broke on that day. But we did manage to achieve this signal here, which is a fantastic observation of the grass of the valley across the hill. Nonetheless, it is first light. This is the first light on our telescope. We now, as of last week, have fixed the new part. We've installed it, and we should be able to get that working very soon. So yeah, there's the controller in question, opened up on the operating table, and it's been sent back to the supplier. It's now fixed. It's back in our hands. It's down in Cornwall. We're ready to go with it. And the wiring is suffering a little bit from the weather, so we've got to clear that up as well. Also, you can't see it there, but the wires have been chewed by the local wildlife, so that's another thing we've got to fix as well. So, as I said, foreshadowing of things to come. So yeah, that's where the project is at the moment. We are very close to achieving first light. We just have to do one more build day and get the wiring in place, and then we'll be ready for first light. The aim of the project is to open it up to amateur astronomers. So we really want to get people involved in this project. We want to start taking observations. We're going to be doing commissioning soon, and when that happens, when commissioning is finished, we'll want to be opening it up to schools, to education, to outreach, to basically people who want to get radio observations at this wavelength. We're very happy to get involved if people want to. Right, xrt-c, done. Next project, the HAB. So the high altitude balloon project is our short project. It only took 1.5 years so far. Yes, that is short in SpaceX times. So we wanted to construct and launch a high altitude balloon. And the idea of it is we want to do, among other things, to actually measure the CO2 profile of the atmosphere as we ascend and descend with the balloon. And a weather balloon is basically, it's something that the Met Office and various other meteorological services launch all the time. It's a balloon with a whole load of instruments attached to it and a payload, and it ascends up through the atmosphere, captures all kind of information about wind speed, humidity, temperature, pressure, all manner of different things that can then be fed into the models every night as they run, and then you can get the forecast the next day. But we're not going to be doing that. We just want to get CO2, and we want to hopefully get it back if we can. Oh, and we want to do all of that without injuring anybody while we're doing it. That is the third major aim of the project. So that is what we want to get. The whole idea behind this, the lofty ambition, is to be able to get this kind of thing here, which is basically an altitude versus a parts per million measurement of CO2. That is the aim. We will hopefully be able to get it, and we'll be doing it with this equipment here. So first we'll be using a latex weather balloon. It's good quality, and it's designed to burst about 30,000 feet somewhere in the stratosphere. So we'll hopefully be getting most of the concentrations of CO2 there. The brains of the whole thing is this Raspberry Pi 3, which is running Raspbian Linux. It's connected to a Pi in the sky, so the Raspberry Pi is this little board under here, which I'm sure a load of you have seen before. And this thing here is the Pi in the sky. Now the Pi in the sky basically gives us access to a load of telemetry. It gives us access to temperature, pressure, and it does a load of communication work for us. So it gives us radio communication at 434 megahertz, which means we can basically chase after it in a chase car and watch where it is in real time. We can also get image data back from it as well, so we'll have a camera on board. And it will hopefully also, when we're finished modifying the software, send us back concentrations of CO2 as it goes up through the atmosphere. So if we do lose it, we may keep some of the data, but please, we hope not to lose it. So that is basically, this is the incredibly overcomplicated setup that I have running with software-defined radio that lets us actually receive data from it. So you can see here that this is like the frequency that we're receiving data at. This is like the timeline here. And you can see just up in that corner, we have an image that was sent back from the camera attached to it. And just in here, it's a bit garbled, but there's a load of telemetry being sent back here, so it sends back telemetry as we're chasing it, basically. So the sensor, the CO2 sensor in question is K30 CO2 sensor. Might not mean much, but it basically can measure a wide range of concentrations of CO2 in the atmosphere. And the nice thing about it is it's a very fast response. It can sample every 2 seconds or so we can very rapidly build up these profiles as we ascend. The whole flight is going to take roughly 90 minutes when we launch it, so this will let us get a very good cadence on our data. The chassis that we're building here is basically to keep all the electronics safe and free, so you can see here is a space for the CO2 sensor, and when we're finished, the Raspberry Pi and the Pi and the Skyboard are going to go in here, and we can run cables between them, and it basically means that we don't risk them flying around in transit and damaging each other, and it gives general protection to them. I said I was apologising. This is one of the reasons I apologised at the start. That's meant to be a picture of the parachute. But basically, yeah, we've got a parachute attached to it as well. It's from Random Aerospace, so it's a good quality parachute, and it should stop our payload from coming down and hurting anybody when we launch it soon. We've done extensive... There you go. There's the parachute there. That one there. And it will slow the payload on descent. We've done a load of testing as we've been doing this, and we've also checked the payload box here. So it's a salmon cube sized box. This is an inside joke, because it looks like a box that you get fish shipped in. And when we were specifying the box on the specification, someone said, oh, it's about the size of a salmon. So it's now become a salmon cubed box. Which has led to the team working on the HAB being called the Fish Squad, because we just send fish jokes back and forth to each other now, because that's what our life is. But it's essentially just a polystyrene box that cushions the inside from being damaged as it's coming down, and cushions the outside, or cushions people on the outside and things from being damaged as it comes down as well. It's got a parachute attached to it, so it'll be descending rather slowly. But we had to check that the box actually flips correctly when we run it. So hopefully, this should be... Is it going to run?
Test the flip. Yeah, okay.
So this is on top of the physics building here. We have our mascots on the bottom, which are 4 little fuzzy bears, which are used for extra suspension. And what we're going to be doing is checking that the box flips. Well, it flipped. The parachute deployed really quite quickly, and had it been given any more space, it probably would have slowed it down. One would hope, anyway.
It looks like it flipped.
Has that gone back? I think that turned out pretty well. Yeah. It hit the ground pretty hard, but we were expecting that anyway, so. Pretty good.
And it flipped.
It flipped.
Sweet.
Yeah.
There's a review of the experiment right there. And just to show that we are also doing our due diligence, there's another experiment here in case it does hit someone.
Yeah, good point, man.
I'm doing something really stupid now, and I'm volunteering as tribute to have the box thrown at me, see if it hurts.
You get so where do you want it?
Anywhere.
Ready?
Yep.
Okay, go. That was more target.
Yes. That's a punch, but it's not that bad.
Okay.
I was lying a bit, it was quite painful. Additionally, just the last piece of this puzzle is this, which is just a buzzer that's attached to a battery. it's very loud. So the idea is that if we lose tracking altogether, but we know roughly which area it should be in, we can just follow the noise of the buzzer and it will lead us directly to the box. It is very loud. Never, if you have any of these, trigger it off inside. You will get some very dirty looks when you do. So at the moment, what's stopping us from launching? We need to check the range on this thing just to make sure that we have a reasonable range that we can follow it. We need a good amount of range if we're to chase it in a car before we can, comfortably launch it. We need to also do a final check on the electronics just to make sure everything is working and continues to be working. And we also need to do last-minute software checking because we've written some software to make this all work, and we just need to make sure that's fine. The main thing that's stopping us from launching next week, say, would be legalities. We have to inform the Civil Aviation Authority that we want to launch. They need to okay it, and they need to tell Exeter Airport not to, we need to check with Exeter Airport they're not launching any planes anytime soon. And that whole bit of legality takes about a month or so. Yeah, so we need basically that time to make sure this all goes through. And we also, the other main thing is finding the right conditions to actually launch, which is incredibly difficult. So, for example, I didn't time it too badly. If we were launching today, that would be roughly where this balloon will be going. As you can see, we've not got much chance of retrieving it if it's out here. Plus, we cannot actually launch it if it's going this direction. So we need to basically use this tool, which is available for free on a website called HabHub. It's called the Predictor. And what it does is it lets you, it loads in a load of meteorological models, and it forecasts where your hab will be flying, given the parameters you put in about ascent rate, descent rate, and burst height. So that's where we'd be going right now if we were launching, and I'm very glad we're not launching, because that would not be a fun trip. One thing that we also have to take into account is we want to actually compare this to something. We want to make sure that our measurement is reasonable. And what we plan to do is there's actually an observatory that's in orbit of the Earth at the moment called the Orbiting Carbon Observatory. And what that does is it captures a column density of CO2 as it goes overhead. And we realize that we have the ability to actually relatively localized in the atmosphere of the Earth capture the profile of CO2 as we go up. So we could then add up our profile, compare it to the column density of the observatory, and then we can actually double check our readings and make sure that they both agree. So if we want to go ahead with that, we need to make sure that the Orbiting Carbon Observatory is overhead as well. So that's another thing we need to consider. So hopefully we'll be launching in late September, early October 2018, ready in time for Freshers Week. We want to try and bring more people into society, so that is the current aim. I say hopefully because there's any number of issues that could stop us, but we really want to try and launch it then. Another thing I just want to bring attention to is, as Wayne mentioned earlier on, we were involved in the Bob Moore Dark Sky application. We actually helped support the application. And so if you're interested in that, please do go and read the application. It's very, very interesting, and it was successful, so we did a good job there, I think. So, thanks for listening to my rambling there. xrt-c is nearly finished, and it's ready to begin. It's ready to begin observations soon, hopefully, when we get the technical issues sorted out. The hab is assembled, it's being tested at the moment, it'll be launching later in the year, fingers crossed. The dark sky application was successful, and as Jack mentioned, thank you for reminding me, we want to be building rockets soon as well. So we want to build rockets and launch them. This isn't water rockets, this is proper solid rocket fuel rockets. And we also want to do outreach demonstrations as well that we can take out to outreach events and show people the wonders of radio astronomy. So, I think that more or less covers it. Thank you for listening, and if you have any questions, please feel free to ask them now.